So what we're going to do with this first couple of examples is we're going to work through the definition, and then we're going to actually see a shortcut. And just like if you saw a geometrical description and you recognised that description would represent a circle, and you can identify from that description what the centre of the circle is and what the radius would be, then you can write the equation straight down. Then we're going to be in a similar position for the parabola. If in the future you can identify the description as a parabola, you're going to be able to use this new format for writing the equation of a parabola and write the equation straight down. So let's see, let's first of all go with the definition, go with our algebraic solution for forming a locus equation, and then in this next example we're actually going to see if we can apply the shortcut. So example 1 says find the equation of the locus of points xy moving so it's equidistant from the point, from this point and this line. The moment I know I'm finding the set of points that are equidistant from a given point and a line, I know I'm finding a parabola. So it's suggested here that we draw a sketch. So let's draw a sketch. And the equation of the locus of points xy, so that the distance from the point 0a, 0a is here. Oh, sorry about that. Now, what do we know? We know that the point is called the focus. We use the capital letter S. I suppose the increment on the y-axis is A, but that point's name would be S. The line y is equal to minus A, so y is equal to a constant, graphs as a horizontal line. We know that would be called our directrix. And we know that this set of points is equidistant from the focus to the directrix. And of course, that then gives us one extremely important point, which we've previously referred to as the vertex, because you can see that point there is equidistant from the point to the line. Then the idea is to find other points, and I think if I draw it rather shallow, it'll be a bit more accurate. The set of points that I've drawn there supposedly should be equidistant. So if I go from here to here, then that distance is the same as that distance. Yeah, I'm going to get a little bit better at that. Or that distance from there to there is the same as that distance from there down. Okay, so it's looking a little bit more like it should. They're asking you to call this point 0a, of course, it would be the focus. The line is minus a, and put on a point P. So let me call this one P, and it's going to be X units across and Y units up. So if it's X units across and Y units up, then we do know we know that this point down here would also be X units across And now if that's y units up, and that is a units down, that would be called y plus a, wouldn't it, that distance? Well, sorry, that's the distance, but that point would be called x minus a. Now, so using the definition now that, as it's described here, we want the locus of points moving so it's equidistant from the point from A to P, and A to P in distance will equal P to B. So we'll set that up. We want our A to P distance equal to our P to B distance. Because distance will involve a square root, then we're going to square both sides. So we will have AP distance all squared, just to remove the square root, and PB distance all squared, squaring both sides. So from A to P, I'm going to use the formula x2 minus x1. So that will be x, I'll do it the long way, x minus naught all in the bracket squared plus y minus a all in the bracket squared. So that distance has to equal P to B, and B we've named as, identified the coordinates as x and minus a. So its distance will be x minus x, obviously there's nothing, plus y minus a is y plus a, all in the bracket squared. Now, I might just pause the video and expand that out and then come back and talk about it. Okay, so you can see that I've written we want those two distances to be equal, which is interpreting the equidistant. We don't want a square root in our calculation, so we square both sides. Using our distance formula for A to P, so we've got x minus naught all in the bracket squared, y minus a all in the bracket squared, and P to B is x minus x, which obviously is going to go to 0. And remember, this distance is y plus a, all in the bracket squared. Expanding those brackets, x squared, be careful with expanding your perfect squares, that goes to nothing, and you get the expansion of this bracket. Now what I've done is what it's suggesting here, which is give your equation with x squared as the subject, because it comes out really nicely, and this is going to be our go-to equation for our parabola in future. So some features, rather than starting having our subject as y, our subject becomes your x variable. It's going to be x squared, as you would expect for a parabola. So it's x squared is equal to 4ay. Now that's going to be, like I said, the automatic equation that you go to when we're talking locus terms and focus and directrix. Because in this format, if we knew, and I guess this is like our very basic, most basic parabola, in that the vertex was here at the origin, and that is the one condition for this basic equation. We'll see a variation just on the very next page of how to adjust your equation, your basic go-to equation, when your vertex is not, and it's very similar to other transformations of graphs that you have seen previously. So I think you'll find it very easy to pick up how to adjust your equation. The nice thing is the 4 always stays a 4. It may not look like 4, but there will always be understood to be a 4 in that position. And what A is your focal length. So there's a lot that we can read from the equation in this format, and in reverse, if we know the graph, then we can use this format to write the equation. Now we're going to see an example of that very thing here in example 2, where we're given a description, we can construct a diagram, and from that we can go straight to our go-to equation and write the equation, fill in the value of a. So it says find the equation of the parabola with focus 0, 2. So you can see that I've graphed 0, 2. What do we know about the focus? The focus sits inside the parabola. And directrix y is -2. What's the directrix? It's, well, because its equation is y equals, it's a horizontal line at -2. We could see then from that the vertex always sits exactly between the focus and the directrix. So we can see for this particular parabola, its vertex is going to be 0, 0. What does this do? This enables me to go straight to my go-to equation. My go-to equation is x squared then is 4ay. The only thing that I need to identify from the equation then is the value of a. From the diagram, the value of a. A, I can clearly see, is going to be equal to 2 because it's the distance between the vertex and the focus. It won't always be the y-ordinate of the focus, because there'll be times when we move up and down the y-axis, or we move totally off the y-axis. But for now, we can see a is equal to 2 straight from the diagram. Therefore, the equation of that parabola is 4, and this is obviously 4 times a. 4 times 2 is 8y, and we leave it at that. I'm going to stop this video here and talk about our extension of our go-to equation in the next video.